So today we move to lecture 68 in the optimization series, and here I'm going to start ant colony optimization, and again I'm Dr. Ranjan Ganguly. So ant colony optimization, also known as ACO, is one more biologically inspired stochastic method, and this method is specially suited for combinatorial optimization problems, which are essentially problems which have a finite number of solutions, typically have discrete design variables. Now, the property of ants which makes them very useful for this method is that they typically find the shortest path needed to go from their nest to a food source. So this is a practical problem which is typically faced by ants, is that they wander around and find a food source, and then they want to bring this food back to the nest, and to do that they need to find the shortest path back to the nest. So essentially they may eat some of the food, but they like to take most of the food back with them for the remaining residents who are staying in the nest. Now, like some of the research we discussed before, the inspiration for ACO algorithm actually came from experiments which were performed on certain ants. And again, whenever biologists perform these experiments, they pick a certain species of ant because different species exhibit different behaviors. So the aim here was to study the science behind their optimal pathfinding capabilities, and an experiment was created such that there was a double bridge between an ant nest where the ants were kept and between a food source. So we will look at two versions of this bridge. One of the versions is a bridge which has the same length. So here you see the ant nest is here, the food is here, and we have these two bridges, that's the double bridge, and both these bridges have the same length. Now, what would happen in this case is that if you have such a situation, after some time the ants tend to take one of the bridges to the food source. So something like what is shown in the figure is what happens. They will take the bridge we have marked as A, and maybe there may be one or zero lone ant which takes the bridge B. Maybe this ant is following a road less traveled or thinks differently, like Steve Jobs. Now, if you repeat this experiment, the probability of selection of any one bridge comes to about 0.5. Now let us go back and think how the ants would start the process. So when ants first start out, the chance of taking bridge A or bridge B is exactly the same. So some ants may go on this path and some ants may go on this path. Remember, at this stage they have not yet found the food, so they are taking any of these paths, and at a certain time they are going to find the food and they are going to try to bring this food back to their nest. Now once the ants leave the nest, they will move randomly till some find the bridge, and then some ants will randomly take bridge A and some ants will randomly take bridge B. So at this point it is completely a random situation. Now one of the things which happens is that ants deposit a chemical known as pheromone when they walk along a path. And they typically prefer to follow a path which has a higher level of pheromone deposit. So when we first start the experiment, there is no pheromone on bridge A or B, so the probability of ants taking both the bridges or any one of the bridges is essentially same, so it is equal to 0.5. Now once the ants discover the food source, they take some and come back to the nest. Now this is a particular habit which is there in ants. And therefore when they go back to their nest, the process can begin on both the bridges, and naturally they will also try to take both the bridges when they go back. All this is random until a situation would happen where a few more ants may take, say, bridge A. Now after this point, the pheromone trail on bridge A will strengthen, making it better for the ants. Remember that ants like to take paths which have more pheromones. And also if bridge B is being taken less, the pheromone on bridge B will slowly start vanishing, and so the pheromone trail on bridge B will weaken. After some time, almost all ants will therefore take bridge A. So this is something which is totally happening by random chance, and we are just selecting bridge A here to illustrate the case. It could as well be bridge B which has become more dominant in this problem. So this is the two bridge experiment with ants, and so after some time we may find that most of the ants are on bridge A. Now if we look at this problem, the taking of one bridge to the food source when two bridges are there and these bridges are of same length is not very smart, and the ants actually may not have done very well in this problem, but there's something to learn here. Essentially we have presented the ants with a trick question because two paths of equal length are rare in nature. In fact, they are not likely at all. So what is going to happen in most situations is that there is going to be one path which is better, and so the method which ants have developed is actually better for a real world setting and not for the theoretical setting which was created here. Ants are also prisoners of the swarm intelligence approach of thinking, which is by putting down the pheromones on the path they travel and then using these pheromones to determine which path to take. Now this really becomes useful when two paths of different length are present, which we are going to discuss next. So here you see the double bridge experiment, and now there are two paths between the ant nest and the food, and here the path A is significantly longer than path B. So in this case, after a certain point of time, the ants are going to take path B, and we are going to see how they are going to come about to this optimal solution. So here a truly optimal solution exists because certainly this path is much smaller than this path, and therefore it is an optimal choice in this problem, which essentially has two solutions. Now in this case, ants once again set out in the random manner. They take both the bridges with the same probability. Here we are presuming that their field of vision is too small compared to the length of the bridge. And the ants which choose the shorter bridge B will reach the food source first and they will come back. And so more traffic will start happening on this shorter path, and therefore the pheromone trail on this path will be more substantial compared to on this path. Also, the pheromone trail here will keep vanishing because less number of ants are traversing that particular path. So when the ant wants to return to its nest, it comes to the point 2 just before the food source and finds the bridge B has a higher level of pheromone due to less pheromone vanishing. Therefore, the probability of choosing bridge B becomes greater. And this process continues. After some time, there is a positive feedback which develops, and more pheromone is put on bridge B, and less vanishing of the pheromone takes place on this bridge B. So essentially there is a positive feedback loop which is created, and after some time most of the ants are going to take bridge B to the food source. And maybe there is one lone ant which is following the road less traveled on path A, but after some time even this ant will figure out that bridge B is the path to take. So we see here that necessitated by nature, there is a urge to choose the minimum path between your home, and the food source. And this is a problem many of us solve in real life when we are, say, traveling from home to a work location, that after some time we do find the best path. Now, many of the softwares which are also there, for example, Google Maps and so on, also try to give you the best path, and they even factor in traffic conditions. So what we now need to do is we now need to create some mathematics to actually see how this particular thing is possible. And we are going to also illustrate a simple and important problem, the traveling salesman problem, in which ant colony optimization can be used. So you can clearly see that there are a lot of problems in optimization where you really don't need to calculate some real number design variables, but actually you need to find the optimal path, the path which is shortest, and so on. So ant colony optimization is very well suited for such problems, and you can see it from the biological behavior of the ants. So in the next lecture, I'm going to discuss how to apply ACO to the traveling salesman problem, also known as TSP. See you then.